So good morning. Welcome to Krishna's classroom again. I am Krishna. The theme of today's lecture is a slight diversion from Riemann integration, although not directly a part of it. It's on Cantor sets, which often is a very mysterious class of points on the interval 0, 1 with fascinating properties. And again, it provides you with wonderful examples. And you know, the real line is full of mysteries, as you will see in this case also. So I have put it as an appendix. It's not directly connected to the theme, but certainly required at some stage or other to discuss certain aspects of Riemann integration. So let us start with it. Okay, what is a Cantor set? So we systematically begin. Let I be the interval 0, 1. And then let 0 less than alpha less than or equal to 1. So we choose a parameter alpha which lies between 0 and 1. Now what we do is we look at this interval 0, 1. We try a magnified form. We remove from it successively a collection of open intervals. Something like we remove first in the first stage. So in the first stage, remove from 0, 1 the central open interval I 1, 1. Now we need the proper notation for it. I'll make some noise about it. Of length alpha by 2. So what we are doing is this is half. We remove from it an open interval. From the middle, symmetric about half, and it is of length, say, you see, half minus alpha divided by 2 into 3, half plus alpha divided by 2 into. So this is the interval that we are going to do. And let me mark that this is the open interval that we are doing. That means not the end points that come here. So we just take this out. Okay. So this we designate by I11. So let me designate this by I11. Now the leftovers, there are two disjoint intervals which we designate by J11 and J12. So we have the following. I11 is defined as the interval half minus 2 alpha divided by 2 to 3 half plus 3. So this is your I11 and the leftover is the following. So you have two disjoint, so this leaves two closed intervals J11 and J12. And each of length each of length 1 minus alpha by 3 into. So these lengths, these intervals are equal to 0 to 0 to half minus alpha divided by 2 into 3 and J12 equal to half plus alpha divided by 2 into 3 comma 1. These are the intervals. Okay. So the upper index 1 corresponds to the first level of activity, and this is what is left over. So I think we will use this index, the upper index, to designate the level of the activity, and then this of course gives two intervals are left, so you put it as 1, 2. That's the notation. So one has to introduce the right kind of notation if you want to communicate mathematics properly. So this is also an object lesson how you do it. So be watching for that also. Okay. So what do we have? We have now 0, 1. This is half. Middle 1/3 has been removed. And then you are left with 2. So this is I11, this is J11 and J1. These are the controls. Now what do you do? Now again, from J11 and J12 you remove the middle portion, each of length alpha by 9. So remove, that is the second stage activity. Remove the central open intervals, I12 and I21, each of length alpha by 3 square from J11 and J112 respectively. So now what you do is you are going in the middle of that and then you move in. So this is the portion that you remove from here and this is the portion that you remove. So you are left with now 4 closed intervals. This one. Shown here in the figure. So what you have removed is this I 2 1. This is the second stage activity. This is also I 2 2. And then you have what remains is J 1 J 2 1 J 2 2 J 2 3 J. That's the second stage. So the first and second stage are fused into this. So what is left is J12 union J22 union J32 union J. Or I should read it properly. J21 union J22 union J23 union J24. So that's the leftover. Okay. So now that's the second stage. Now the third stage is the general one. Suppose at the end step we have obtained to the power n intervals Jn1 Jn2 Jn to the power, so that when n equal to 1, what do you get? N equal to 1, 2 to the power n is equal to 2. Therefore, you get J1 1 and J1 2. For n equal to 2, you get 2 to the power n is equal to 4, and therefore you will get J21, J22, J23, J24. Okay. Likewise, you have at the end stage, suppose you get this. Then you go to the n plus first step. Now each of these A and J is of length 1 minus alpha by 3. That's the first stage you have removed, and then the next stage you have removed, etc. And eventually you have removed 2 to the power n minus 1 alpha by 3 to the power n. This is what you get. So that when n is equal to 1, you get 1 minus alpha by 3. When n is equal to 2, you get alpha by 9 here, and you get 2 to the power, and actually 2. So 2 into alpha by 9. So 1 minus alpha by 3 minus 2 into alpha by 9. Okay, so that's what you get. So you see that, and then you can actually find out what is the length of each of these intervals. It's quite easy to find out. So now the next level of activity is, having obtained this, what we do is remove central open intervals This is the n plus first stage of activity. And that would leave behind J's. This is new. So we have 1 less than or equal to k less than or equal to 2 to the power n, each of length alpha by 3 to the power n plus 1. From each of where of course to obtain j n plus 1k one less than or equal to k less than or equal to 2 plus 1. So successively you keep removing the middle portion, an interval of length, earlier alpha by 3, then alpha by 3 square, alpha by 3 cube, etc., etc., etc. From each of these j's perspective. Okay. So eventually what happens? If you keep removing this, now you see that much of the interval 0, 1 will get wiped out. Okay, so this is what happens. So let us introduce some notation. Let an define union of n equal to 1 to 2 to the power n minus 1 I j, and that is the union of intervals removed at the stage n minus 1. Okay, and then Bn defined by union k equal to 1 to 2 to the power n and we write C alpha as the intersection of Bn, which is essentially 0, 1 slash union one to infinity a. Now one of the things that you observe is make some observations that ANs are all and BNs are closed intervals. These are the two observations that we make. Therefore, now you see that because they are union of finite union of open interval, this is finite, finite union of closed intervals. Okay, and look at this one, C alpha. What is C alpha? C alpha is the intersection of all bns for n running from 1 to infinity. So it is a countable intersection of closed sets. Therefore, C alpha is closed. You can argue it this way: 0, 1 is closed, and it is a complement of union n equal to 1 to infinity of an, which is open inside the closed interval. Therefore, this is closed. So it follows that C alpha is a closed subset of So these are the information that we have on C alpha. Now what next? So we have got this JIs, and then these things are there. Now so what have we got? We have actually perforated the interval 0, made a lot of holes in it, and there is a certain set that is left over towards the end, which you call C alpha. This is a closed subset of the interval, and this is what you call the Cantor set. So we also have the description of AN. AN is those points removed stage from the leftover of 0, 1 after the end stage. Now Bn is the set of points left over after the n plus first stage removal has to be completed. And then C alpha is the set of points left after all the intervals I, N, J 1 less than equal to j less than equal to 2 to the power n, and C alpha is a closed set. And the set C alpha is in fact the alpha is a parameter. Okay. One special case of interest is if alpha is equal to 1. When alpha is equal to 1, what you do is you start with removing the middle 1/3 of the interval 0, 1, and then the middle 1/3 of the two leftover intervals, then again the middle 1/3 of the leftover intervals, and so on, and eventually after removing everything successively, what is left is what you call C1. So C1 is the traditional Cantor set. So this is in a way a generalized Cantor set. There's a something very special about the C1, which is traditionally known as the Cantor set, and this is a generalized Cantor set. Okay, so let us explore the properties of this particular set. So one observes from what we have done the following. Okay. You have the interval 0, 1, and you have removed the middle one from here, and therefore you see that these points are certainly in the Cantor set. Okay, the boundary of the middle 1/3 interval or middle alpha by 3 interval that you have removed is in the Cantor set. So the Cantor set is non-empty. Okay, so let us start exploring this. Okay, so the first property is that, because we have already observed that C alpha is closed, we'll make once again compare that. So first of all, you observe C alpha is not, because you can easily see that the C alpha includes the endpoints of all the open sets I and J from 0. Therefore, it is not. The second property that we would like to establish is what is the length of the total length of the intervals that you have removed. So the sum of the lengths of intervals removed from I, that is equal to 0, 1, is the sum of all these intervals where they are disjoint intervals. Therefore, this is essentially equal to sigma 0 to infinity alpha 2 to the power n by 3 to the power n plus 1. And this you can show that this is equal to alpha. So essentially it is alpha by 3 into 2 by 3 to the power summation of this. Okay, let us explore this. It's quite easy to see what goes on. When n is equal to 0, when n is equal to 0, the length of the interval removed is length of so for n equal to 1, what do we have? You have alpha by 9 removed. So what you have is, see, when n equal to 1, see, you have alpha by 3, this is actually alpha by 3 plus n equal to 1, there will be one more term that it comes. So it is going to be alpha by 2 by 1 by, so n equal to 1 is going to be 2 divided by 3 square. Or you write this alpha by. So this one already removed an alpha by 3 as a first stage, and then you remove this. And then you keep on removing the steps at each stage. So that's how you get this eventually. And this is a convergent infinite series, and you can easily show that the sum is actually equal to. Okay, so that's simple. Right. These are the main stage. The third problem is, if then C alpha cannot be covered a countable collection of subintervals of total length and we remove the whole lot of thing eventually. So this is what you get. This is the set of or the length of the interval that has been already removed eventually. So what is left is the total length minus alpha. So this is what it says. So you cannot cover it. So the leftover has a content, you would like to call that content. I don't want to call that the length, because we have not introduced the concept of length for non-intervals. So what is left is a non-interval. Okay, therefore you cannot talk about the length. It's a set of points. Okay, so you call the content of that as 1 minus alpha. So this is the total length. I just okay. This is all right because I am talking about subintervals. But therefore, the length of, or what you call, I will put it in inverted commas because, or what you call content. C alpha is 1 minus alpha. Okay. It's a set of points. Okay. Now the fourth thing that you prove is C alpha for alpha less than 1 or alpha not equal to 1 cannot be a null set. Okay? Because after all, what is left over has length something like 1 minus alpha. ಅದೊಂದು ಸ್ವಿಚ್ ಆಫ್ ಗೆ ಬರೆಯ ಅದೊಂದು ಸ್ವಿಚ್ ಆಫ್ ಗೆ ಬರೆಯ So what we already know is that 0, 1 is compact, and by definition C alpha is closed. Therefore, which implies C alpha is a compact subset of that is another observation. Now the fifth observation we make is the following. Take the special case alpha equal to 1. And alpha equal to 1, you have C1. Now what we can show is that C1 is a null set. That means it can be packed into a countable collection of intervals whose total length can be made arbitrarily small. So let us just look at this property. So let epsilon positive be given. Now we choose a positive integer sufficiently small, sufficiently large, so that sigma k equal to n plus 1 to infinity 2 to the power k minus 1 divided by 3 to the power k is less than n. This is the tail of the series that we are looking at. So the tail of the series is kept less than epsilon. Then we see that the finite number of intervals j n k for 1 less than or equal to k less than or equal to 2 to the power n C1. We are talking about C1, not C alpha. Thus, for alpha, this is obvious. For alpha equal to 1, C alpha is an answer. And one remark that you immediately have is that C alpha is not a null set. For 0 less than alpha less than 1, C alpha is not a null set. But we have seen that the C alpha has content, or later we call this measure, although we have not defined this yet, 1 minus this. That's it. Okay. Now, one more interesting property for C1 is that C1 is not a countable set. Okay, I mean, it will give an impression that this is a countable set, but it's not really. This is the interesting part. Now we can prove this. So C1. So what is C1? So C1 is not countable. What is the implication of this? C1 is an uncountable set of points. At the same time, it does not have any intervals in time in it, that we will see soon. And having the property that it's a null set. Okay, so this is an example where even uncountable sets may be null sets. Okay, because we have earlier proved that all countable subsets are null sets. Okay, so here is an example where an uncountable set could also be a null set. Okay. Nevertheless, so let us first prove that it is countable. It's a very curious proof. So what is C1? We take the consider the ternary expansion of elements in C1. Now, if you take C1, what happens? The first stage you remove the middle one third, opens it. Now, if your alpha happens to be the first one, then you say this is point. So this you designate by 0, this you designate by 1, this is you designate by 2. Then it is the first, if it is going to be here, we designate the first place of the ternary expansion as 0. If on the other hand it is here, then you designate it as 1. If it is here, then you designate it as 0.2. Then what you have? So you have removed this. So what is left? So you see that what is left at this stage has ternary expansion starting from 0 or 2 only. Okay? And you do the same thing and remove the middle one third. So you go to the next ternary expansion. So you have on this part, if it is here, then it is 0. If it is here, it is 1. It is here, it is 2. Therefore, you get either 0, 0 or 0, 2. And coming to here, it will be 2, 0 and 2, 2 that you have. Therefore, you eventually see that the sets of elements, each element of C1 has a ternary expansion .A1, A2, etc., where each AI is either 0 or 2. Okay? This is the ternary expansion. Or in other words, your X, the element X belonging to C1 is of the form sigma n equal to 1 to infinity an by this way. So what one has is, you see, suppose you have listed all these numbers, then assume that it is countable, then you can list them, one after another, and then you can construct a new number from it. How do you choose the number? So that number can be chosen as B1, B2, etc. So it is B1 is equal to 0 if A1 is equal to. Okay, so you list it like this. So you have, suppose you have listed this x1, x2, etc. So then this is equal to point. And so on. And all the AIJs are either 0 or 2. So now you construct a new number y this way. Make it different from x1 by choosing it as 0 point. If A11 is 0, then you write 2. If A11 is 2, then you write it as 0. So that you make sure that y is different from x1. Similarly, go to the second place and then you can make it different from x2 and so on. So you can construct a y eventually which is different from each one of these. Okay, so your assumption that's countable and we have exhausted by listing them out is violated. So that leads to a problem. expansion. Therefore, it is uncountable. And there is another way of seeing the whole thing, because as I said, you see that you have, the x listed as 0.a1, a2, because ai is equal to 0 or 2. Now you construct another x tilde as 0, a1 by 2, a2 by 2, etc. So they are going to be either 0 or 1. So it is going to be a binary expansion of certain number. So this is of certain number. Therefore, you can define a map from C1 to the interval 0, 1. Okay, this is in the binary form. This is in the and then show that the mapping x to x tilde is a 1-to-1 onto map from C1 to. Now you know that the interval 0, 1 is uncountable, which implies C1 is uncountable. This is uncountable. So you need to fill in the gaps. So this is eventually what you get. Okay. So it's an uncountable set. It's uncountable. Nevertheless, C1 has the total content of the measure equal to 0. Now that's something very fascinating, and that is going to give us a lot of interesting examples. Okay, so that's the whole purpose of this. Now I will just go into the further properties of this probably in my next lecture. But the whole purpose of doing this Cantor sets is that it can give you very fascinating, incisive examples to study the properties like Riemann integrability and many other things. So this will give you a wealth of examples. So that's it. Thank you very much. Stop here.